If you can hear me, if you can see me, if you can hear me, if you can see me, please say, please type in clear. Please type in clear. We are going to do one of the most important chapter, waves. We are going to do one of the most important chapter, waves. Many people are going to feel that this chapter is a bit difficult. No, it is not. If you are going to be, if you can understand this chapter on a very basic fundamental level, then this chapter is very easy to score marks. Trust me, see this lecture, I'll show you. I am going to, meanwhile, please type in clear. If you can hear me and if you can see me, please type in clear. Look, I have some animations ready actually. I'm going to show those things to you. For example, look, I have kept one thing. You see, when I start it, can I zoom it in? Yes, we can zoom in. You can see there are some simulations ready for us. There are some simulations ready for us. You can see there is a wave, right? No end. So I have many things. I have many things kept ready to show all these things to you. I have many things ready to show all these things to you. So all of them are ready. Just type in clear. We will start. Okay. Okay. People have said clear. So we will first deal with basic things like what is a wave and all that stuff. Then we will see some animations and all that. Okay. So first of all, what is a wave? Before we start dealing with what is a wave, I would like to just talk about, let's take a particle. If that particle is having some kinetic energy, so wherever the particle is going to go, it is going to carry that energy along with it or not? Yes. So one way of transferring energy from one location to other location is going to be making the particle having energy to go there. So whichever particle has that energy, it should go over there. Okay. Now, one other way is going to be without the transportation of the medium, but energy is going to get transported. That's what is a wave motion. For example, whatever I speak right now, right? So there are air molecules in front of me. So whatever I speak has created a disturbance in these air molecules. If that disturbance is going to carry the air, if it is going to carry away the whole air, after some time there won't be any air around me, then it will be difficult for me to breathe because there is no air around me. But is that happening? No, it's not happening. It's not happening. That's a clear indication that whatever the disturbance I have created in the surrounding medium is not carrying that medium away. Disturbance is moving. How I know disturbance is moving? Whatever I speak is heard by many people around me. But the medium is not totally taken away. So wave is one such thing which is going to be transporting energy from one location to other location without transportation of the medium. Wave is a disturbance. Wave is a disturbance which transports energy from one location to the other, without transfer of medium. Without the transfer of medium. That's what is going to be called as a wave. Okay. Now I see that medium should not get transferred. but energy should be moving. And whenever I am going to create a disturbance, definitely the particles around me are going to get disturbed. How I know that the particles are going to get disturbed? Because the particles are going to move. Now, it is very evident that the particles have to move. Particles have to move, but they should not get, excuse me, but they should not get transferred. What is that motion which we have learned where the particle will move but it will not get completely displaced, but it will not get completely displaced? It's oscillation, right? In oscillation, what the particle does, the particle is going to be oscillating to and fro, but it is never going to get completely displaced. So now I realized that without the transfer of medium, but if the energy has to get transferred, that means we are talking about many particles oscillating. Many particles which are going to be oscillating. So one thing which I realized is that the particles of the medium should oscillate. There will be many particles. Keep that also in mind. There will be many particles which are going to be oscillating when the disturbance is going to be propagating. Okay, fine. Then how many types of waves we have? It depends on how do we classify them. So if we are going to classify on whether they require a medium or not, then we classify them into requirement of medium, based on the requirement of medium. If we are going to be classifying the waves, then we classify them into mechanical and non-mechanical waves. Mechanical waves need medium. They need medium to propagate. If you ask me examples, one best example is going to be sound waves. Sound waves definitely need medium. Non-mechanical waves, they don't need medium. Non-mechanical waves, they don't need medium. So what are those things? All those electromagnetic waves, for example, visible light, everything, all those electromagnetic waves, they don't. That's why the light that is produced at sun is reaching earth, although there is nothing in between earth and sun. There is pure vacuum. Okay, fine. But there are few more classifications which we need to know. What did I tell you? I said that wave is a disturbance which is going to carry energy from one location to other location. Sometimes what will happen is there will be two waves, equal and opposite waves. Then this wave is carrying energy in this direction. This wave is carrying energy in this direction. So the net transportation of the energy will be what? Zero. So based on whether the energy is going to get transported or not. Based on whether the energy is going to get transported or not. Based on energy transportation, we can classify into progressive, or sometimes also referred to as traveling waves. Sometimes also referred to as traveling wave, where energy definitely gets transported from one location to other location. And there will be one more situation where there will be a disturbance, but net transportation of energy will be zero. So those waves are called as stationary waves. Stationary waves are also called as standing waves. So generally standing waves are going to be produced by definitely two equal and opposite waves traveling in two equal waves traveling in opposite direction. Two equal waves traveling in opposite direction. Okay, fine. Next, we are going to classify it into based on movement or oscillations of the particle. Based on oscillations of particles in the medium. Based on oscillations of the particles in the medium. So we classify them into transverse and longitudinal. Transverse waves and longitudinal waves. So how are we going to decide these things? See, in transverse wave, if the disturbance is traveling in this direction, particle will be oscillating perpendicular to the direction of propagation of energy. In longitudinal waves, if energy is propagating in this direction, particles will also be oscillating in the same direction. Particles will also be oscillating in the same direction. Those are called as longitudinal waves. For you to understand, I have picked, okay, I forgot. Actually, I picked a GIF file and Note is going to convert everything into PDF. I lost it. Fine. Look, if I am going to talk about all the particles which are going to be over here, can you see these things? Those dots, hard. Let me take red. All these particles, what they are going to do? In longitudinal waves, right, energy is going in this direction and even the particles are going to be oscillating along the wave. So basically these particles are going to be oscillating like this. As a result, when the wave is going to be moving, you will have particles crowded. These are called as compressions. And you will see a region where there is lot of separation between the particles. Those are called as rarefactions. And these are called as compressions. And now when we talk about a transverse wave, this particle, whatever is there, is going to go up, come down, go down, come up. So how is the particle oscillating? Means the particle is oscillating up and down. The particle is oscillating up and down, but the wave is propagating in this direction. So in these kind of movements, we call it as transverse wave, where the particles oscillate along the direction of propagation of the wave is going to be called as longitudinal wave. Next, here we call these things as crests and we call these things as troughs. So in transverse waves, we will have crests and troughs, and in longitudinal waves, we will have compressions and rarefactions. Okay, fine. Now, we need to know on what parameters the wave is going to be depending on. So, when I am going to be talking about multiple particles of the medium, when I talk about multiple particles of the medium, see whether it is going to be transverse wave, whether it is going to be longitudinal wave, no matter what we are talking about, they will be oscillating. So different particles are going to be at different displacements from the mean position. Different particles are going to be at different positions from the mean position. For example, you take this transverse wave only. Let me talk about this particle and let me talk about this particle. So this particle is at a height of, let's say, some y1. This particle is at a height of, let's say, some y2, right? y1 and y2. Okay, that means at the same time different particles can have different displacements. So now, if someone is going to ask, what is the displacement of a particle, then the immediate question by us is going to be, which particle you are talking about? Because in a wave, there are many particles. As there are many particles, so you have to be precise on which particle you are going to talk about. Yes. So then they are going to give. They are going to be like, what is the displacement of a particle which is at some x distance? So at x distance, definitely there will be one particle, and that's the particle we are talking about. Now, for example, if we take a transverse wave, how this particle will be moving with time? It will be going up and down, right? It will be going up and down. So even though I talk about the particle which is at x distance, will it stay there? No, it will be continuously moving. So as time changes, displacement of the particle will be changing or not? So if you are going to talk about displacement should be a function of x as well as t for a wave. Why? X is going to give you information about which particle we are talking about, and t is going to be talking about time. And what does t give us? If you put t as 1, then it is the displacement of the particle which is at x distance at a time t is equal to 1. So we have complete information now. So wave, unlike SHM, if you remember SHM was y is equal to a sin omega t, y is equal to a cos omega t, y is equal to a sin omega t plus pi by 3. So in SHM, all you need is time. Because in SHM, we were talking about a single particle. So now, in waves, we are talking about many particles at different times. So we need x as well as t. Now I am going to give, without any proof, some information. I will prove it in this class only, but after some amount of time. Look, for a traveling wave, y is going to be f of plus or minus x plus or minus bt. So basically in the same argument, you should have both x and t added or subtracted, or both having negative sign or both having positive sign. So x comma t should be in the same argument. I will prove this one. Don't worry. I'll take away all the conceptual doubts you have. I'm going to do the basics with the derivation. Don't worry. I will make sure your concepts are going to be very, very, very strong. How I think, I'll make you think like me. Whatever have helped me, yes, definitely I'll give it to you. Now, for standing wave, just keep this in mind. X and t will not be in the same argument. That means x and t will not be there in the same function. So it is going to be like this. Y is going to be f of ax some g of bt. Like in two different arguments, x and t functions are going to be there. So if you see two different functions having one having x and one having t, that's a clear indication that we are talking about standing wave or stationary wave. And without proof, I would like to give one more statement. As I said, I will be proving it later. See, from these expressions, we can calculate the speed of the disturbance. See, whatever I speak, I created a disturbance, and the disturbance is traveling in all the directions, which is nothing but called as sound wave. So the speed at which this disturbance is going to travel is called as wave speed. So how we are going to get wave speed? We get the wave speed is, what is the wave speed? It is going to be the magnitude of coefficient of t divided by magnitude of coefficient of x In this case, the magnitude of coefficient of t is b, and in this case, the magnitude of coefficient of x is what? A. This also I will be proving it in this class, but just accept it now. Just accept it now. Okay. Now look. Let us talk about a specific type of wave called a sinusoidal wave. When sinusoidal waves are going to get produced, sinusoidal waves get produced when particles of medium undergo SHM. And let me tell you, in our syllabus, majority of the times, very rarely, out of 200 questions, 1 or 2 questions will be there on those waves which will be testing your basic understanding of waves. Rest all are going to be sinusoidal waves. That's why in our syllabus, we will have oscillations first, that is SHM first. After SHM, immediately we will have waves. So there are many types of waves. In general, how the waves are going to look like, that also we will talk about. But first, let us deal with sinusoidal waves. First, let us deal with sinusoidal waves. What are sinusoidal waves? Those waves in which the particles are going to be executing SHM. Now the time has come for me to show you animations. Now the time has come. So I'll show you, right? But a small recap which you people should have in mind is that if there is a particle which is going to be executing SHM, it should be some A sin omega t plus phi, right? Or theta. The displacement of that particle is going to be given by this. Displacement of the particle is going to be given by this. Keep that in mind. Okay, man. And second thing is that if I talk about a particle which is oscillating in the y direction, and at time t is equal to 0, it is at mean position and moving up. That means to the positive y. If it is moving towards the positive y at time t is equal to 0, when you look at the particle, if it is at mean position and if it is going up, then what will be the equation of that SHM? I did oscillations to you. See, it should be y is equal to A sin omega t, right? And at the time t is equal to 0, it's at the mean position and moving towards the negative and moving down. Moving down means what? Towards the negative y. Then what will be the equation? Y is going to be minus A sin omega t. Use your common sense, you will understand. Look here, as time increases, omega t increases. If omega t increases, angle of sine is increasing, then sine will increase. That means y value will increase. Yes, proper. If it is going to the positive side. Now the same explanation, minus A sin omega t. As time increases, omega t increases, sine increases. As a result, negative value will increase. That means it will be moving down. So if it is moving to the positive side and if it is present at mean position at time t is equal to 0, this is the equation. At time t is equal to 0, if it is at the mean position and moving towards the negative side, then minus A sin omega t. Okay. Hey Karthik, how are you, man? Don't think that it's a what we call premiere. No, this is for sure not a premiere. Now there will be many people who will be having doubt, man. There will be many people who will be having doubt. Like, if y is given as a sin omega t minus kx, if y is given as a sin omega t minus kx, how did people say that it's a wave traveling in positive x direction? If y is a sin kx minus omega t, then also it's a wave traveling in positive x direction. If y is going to be a sin omega t plus kx, then it's a wave traveling in negative x direction. These kind of statements have been given to you, if you remember. We will exactly find out why. We will exactly find out why. Let us go for, oh, just a second. It's too fast, man. Ding. Now you see. You have to see exactly how I am going to be looking at it. You have to see how I am going to be looking at it. My request to you is that, 1 second. Can't I pause this one? I can, right? Okay. Here I have. Now look, man. Just concentrate only on this green dot. Just concentrate only on this green dot. And tell me what the green dot is going to do. If you look at only the green dot, look, man. I'll put it in slow motion for you to understand better. Look at it. What is it doing? It went up. It's coming down. And then it is going up. It has done one oscillation. And how did it go? It went from t is equal to 0. It went to the positive side. It went to the positive y. And by the time one oscillation is completed for the particle, can you see that the disturbance has traveled some distance? All these particles got disturbed. I have paused, I have freeze the time. That's why you have this shape. Otherwise, actually, these particles are going to be moving. All those particles are going to be moving. And second thing is that how much ever disturbance is going to get created in one oscillation is called as one wave. And length of that wave is going to be called as wavelength. So what happened over here? 1 second. Let me write it. Let me draw it here. So by the time one oscillation has been completed, I got something like this. So this has completed one oscillation. One oscillation has been completed. Whatever the length I am going to get, that's going to be called as one wave, and it is also going to be called as one wavelength. It is represented with the symbol lambda. Now you only tell me how much distance the disturbance has traveled, lambda, in how much time, in one oscillation of the particle. One oscillation is going to take how much time? Capital T, time period. So can I say wave speed? Can I say the wave speed represented with V is going to be the distance it has traveled divided by the time, lambda by T. So this is how the wave speed lambda by capital T has come. Okay, let us go back. Let's see how much our data we can get. Now look, man, disturbance has just reached this point. Disturbance has just reached this point. Look at that point alone. What is that doing? What is that particle doing? You see that? You see that? It is also oscillating up and down. And one thing which I want you to realize is that by the time this completed one oscillation, how much wave is in front of it? One wave. And by the time this completed one oscillation, how many oscillations this has completed? 2 oscillations. That means if a particle completes 2 oscillations, there will be 2 waves in front of it. And if a particle is going to complete 1 oscillation, there will be 1 wave in front of it. If a particle completes half oscillation, there will be half wave in front of it. 1/4 of the oscillation, 1/4 of the wave in front of it. That's it. As simple as that, man. As simple as that. Now, let me restart the whole thing. Are all particles having same amplitude of oscillation? Let us look at that. Let's see. See, this is the one which is in our hand. We are the one which are making this one move with the help of some external agent. So this external agent is continuously giving energy to this one, and that energy is getting transferred without the transfer of medium. Okay. Now this green one, let's say, has gone till here. Oh shit. Can you see all of them? 1 second, look. The green one went maximum up to there, and rest all particles are also having the same maximum from the mean position or not. You see, what does that mean? All the particles of the wave have same amplitude. Okay, that is one observation. Now I have one more question. Will all of them have same time period of oscillation also? How do I know that? See, if this completed, let us play it. By the time this completed one oscillation, right, we got one wave. So if this one and if this one have same time period of oscillation, then by the time this completes one oscillation, even this should also complete one oscillation and come back to the same location. Let us observe. So it went up, it's coming down, right? It is going up. By the time this completed one oscillation, look at this. It is exactly at the same position and repeating the same thing. What does that mean? This one and this one were having same time period of oscillations. Like that you compare this. All the particles will have same time period of oscillations. Okay. So nice. Now, there is a clear-cut difference between wave speed and particle speed. Wave speed is the speed at which disturbance is going to move. Particle speed is the speed at which the particle will be oscillating. Wave speed is constant, but particle speed is not going to be constant. You know that the particle is executing SHM. Particle is going to be having maximum speed at the mean position, zero speed at the extremes. So this is one place where majority of the people get confused in waves chapter. They don't differentiate between wave speed and particle speed. Wave speed is the location. Wave speed is the location where the speed at which the disturbance is moving. Particle speed is the speed with which particle is moving. Let us see that. See, the disturbance is traveling, right? Disturbance is traveling. Okay. Now look, observe one particle. Let us look at this green particle. It is at rest. Now when it is going to the mean position, it moved with greatest speed. And again, greatest speed it is crossing. Slowly it is coming to rest. Again its speed is increasing. And then again it is coming to rest. Again its speed is increasing. So now again it came to rest, increasing, crossing the mean position with maximum speed. One more observation which I want you people to know is that, man, when it is crossing the mean position, can you see the separation between the particles? Look at the separation between the particles. Is the separation between the particles maximum? That means the elastic potential energy is maximum. So when the particle is crossing the mean position, its potential energy is maximum, elastic potential energy is maximum, and even the kinetic energy is also maximum because it is moving fast at the mean position. So in waves, elastic potential energy is going to be maximum when the particle is crossing the mean position, and its kinetic energy is also maximum when it is crossing the mean position. It is slightly different from SHM. Slightly different from SHM. And one more thing, when it is at the extremes, you see the particles are very close, indicating the gap between them or the separation between them is not too much. So the elastic potential energy is lowest at extremes, and even kinetic energy is also lowest. So one important point which you people should know, that the elastic potential energy and kinetic energy are going to be maximum at the same time, that too when the particle is crossing the mean position. That too when the particle is crossing the mean position, right? And when the potential energy and kinetic energy are zero, when it is at the highest point, that is at the extremes. Okay, next I would like to give you few more interesting results with this simulation. Few more interesting results. Okay, man. Okay. You think wave as a message which is being sent by us. We are this. We are this one who is giving the message to this green particle. Green particle will give the message to the red one. The first red will give to the second red will give to the third red will give to the fourth red, and so on. What is the message which I am going to send is that I am asking this green to go up by 1 centimeter, and then 2 centimeters, and then 3 centimeters, for example. Now you look, the first message this has got is 1 centimeter, and the next message is 2 centimeter, and the next message is 3 centimeters. So we have a sequence of messaging. What is that sequence of messaging? The first message sent was go up by 1, and then the message was go up by 2, then the message was to go up by 3. Now look, this particle gets the first message, then the second message, then the third message. Look, it will go up by 1, then 2, then 3. Now if you look at this particle is yet to get the first message. It has got the first message now, and it is going to go up by 1, 2, 3. Like that, if you see, there are particles which haven't got any message at all. And if they are going to get, what is the first message they are going to get? Go up by 1, then by 2, then by 3. So we are continuously sending a message kind of thing, right? From where it is getting the message? It is getting the message from the previous particle. So why did I teach you this? Why did I teach you this? Because they are going to give a frozen diagram like this. They're going to give frozen diagrams like this. They freeze the time and they give this shape, and they are going to be asking whether this particle is going to move up or down. With this shortcut which I am teaching you, you can easily identify whether it is going to move up or down. Whatever the message it gets from the previous particle, it does that. Am I right? Whatever the message it is going to get from the previous particle, it is going to do that. Now look, how this particle will behave means whatever the message it is going to get from the previous particle. What is the previous particle? This is the previous particle, which should be treated as previous particle. The particle where the wave has reached first. As it is a wave traveling from this side to this side, so it's a wave traveling in positive x direction. It's a wave traveling in positive x direction. So in that situation, if I talk about this particle, before reaching this particle, wave has reached this particle. So how this is going to move means, you look at its previous particle. If the previous particle is up, then it will send a message asking it to come up. If the previous particle is down, then the previous particle will send a message asking it to go down. Right? Now look, I will unfreeze the video. Look at what will happen to this one. With the concept which I have given to you, As the previous particle is up, the message that it is going to send is to come up. Let's see whether that particle goes up or not. Did it go up? Yes. Now look, let us talk about this particle. For this particle, the previous particle will be this. How to choose the previous particle? The particle where the wave has reached first. Obviously, wave has reached this particle first. So for this particle, this one is the previous one. And for this green one, this one is the previous one. So the previous one is down. So the previous one will ask or send a message asking it to come down. Now look, when I play the video, is the green particle, did the green particle move down? Yes. Now the green particle has to move up because the previous particle is up. Is it moving up? Yes. Now I will randomly pick any particle in this wave. I will randomly pick any particle in this wave. Now, Mr. Karthik, don't worry about whether negative marking is there in section B or not. If it is there, it is difficult for everyone. In fact, I was talking about this in the Vedanta Telugu channel. If you remember, I said, as far as I remember, there was negative marking. As far as I remember, there was negative marking. It's good. It's good only, man. Up to 2 decimal places you have to mark. Right? Anyway, whether there is negative marking or not, if you are conceptually strong, you are going to make it. You don't need to worry about negative marking. If you know it, you mark it. Otherwise, you leave it. It is good. I'm telling you, it is good for you people. Why? Those who have access for quality teaching, now as the paper is going to be having decimal places and that too negative, people will be scared to attempt. So that means out of 25 questions, might be people will attempt 20 or 18. So the marks will go down. When the marks are going to go down, you have the liberty to leave the difficult chapters, man. You can learn the easier ones and the moderate ones. You score some 15, 16 questions. You do 15, 16 questions correct, your percentile will be good. That's actually a good thing. Pray to the God that the paper should be difficult. Pray to the God that everything has negative marking. Pray to the God that the numericals are going to be difficult. MCQs are going to be difficult. What is the advantage of that? You don't need to prepare 100% of the syllabus, just like JEE Advanced. Just like JEE Advanced. So just pray to the God that it should be as tough as possible. It should have as many negative markings as possible, as complicated as possible, so that you people are going to be ahead of others. Or if the paper is easier, what happens in board examinations? What happens in board examinations? In board examinations, everyone are going to be getting 95% of marks because the paper is easier. Look at JEE Advanced. If you get 60%, 50% of marks, your rank will be below 2000. That's how it should be. Come on, that's good. Don't worry. Okay, now. So one thing, the shortcut which I have given to you is that you look at the previous particle where the wave has reached. Depending on the previous particle, you can predict how the particle is going to move. For example, if I talk about this particle has its previous particle down. So when I unfreeze time, this particle will be moving down. You observe. Did it move down? Yes. Okay. So one more observation, one more difficult thing which is hard to process has been done. Now, one more observation, a very important observation. What is it? See, when the message is being sent, it takes a while for the message to go. How much? Well, it depends on the wave speed. So the person who is running with the message, whoever is going to be running with the message, that person will be having some speed. What is the speed? Wave speed. Now look, this green particle is having maximum displacement at this point of time. Now it will send a message saying that you have maximum displacement. Let's take the maximum displacement from mean position to be some 3 centimeters. Let's take it. Right? Now you see, man. So first message is going to be what? Go up by 1, then by 2, then by 3. Now the message is 3, and that 3 will take some time to travel. Let us play the video. Let us play the video for some time. Time is getting elapsed. Now look. At time t is equal to, let's say, 1 second, that first 3 message was sent. Now, after some time, this particle is having that displacement or not. So whatever the displacement this particle was having some time back is the displacement of this particle or not. Why it is having after some time? Because the message created by this takes some time to reach this particle. So when the message reaches that particle, that's when the displacement of the particle will be 3. So whatever the displacement this particle is having, this particle had the same displacement but sometime back. Very important statement. I hope every one of you have understood what I'm talking about. Aerospace IITN, sir, have you completed full modern physics? No. I have nuclei and then semiconductors. So next week is going to be nuclei and semiconductors. So 1 week 12th, 1 week 11th. That's how we have planned in ROAR series, is what is said to me. Okay, fine. It's good. 22nd of Jan to 31st of Jan. Good. It's a good thing. Now look, man. So what I have clearly shown you, the displacement of this particle at this point of time is the displacement of this particle some time back. How much time back means you can easily calculate with wave speed and distance. Come on. Time has come. People have to become serious. Come on. So now I will just go for teaching. Okay. Now I want to talk about wave equation. I'll talk about wave equation. But before that, I would like to add up all the points, whatever I have given. All the particles have same amplitude. All the particles will have same amplitude and time period. Same amplitude and time period. This is one observation. Okay, next. This is where you will get a lot of conceptual clarity. You will understand how those wave equations have come. Let us take this particle to be at x is equal to 0. And this is the one we are moving up and down. So by the time this goes up, we would have 1/4 of the wave. And by the time it has come down, we will have 1/2 wave. And then I am drawing the complete wave. So whatever the particle is there at x is equal to 0, how did I make it move? I made it move up. So I can simply say that the displacement of the particle which is at x is equal to 0 is going to be given by this. Agreed, sir? So as more and more time is going to be elapsed, you'll have more and more waves getting created. Right? Now what I want is I want a displacement of this particle. I want displacement of that particle, which is at some x displacement at time t. Man, I have no clue about it. But one thing I know, whatever the displacement this particle is having at time t is displacement of this particle some time back. Who gave the message? This is the one who has spread the message. How much time the message takes to go? It takes x by v time. So displacement of particle at x at time t is equal to displacement of particle at x is equal to 0 at time. At time, how much this is t time, right? Some time back. How much time back? So the wave takes x by v time to reach here. That means at time t minus x by v. We are asking at time t. Now we have to go back in time. How much we have to go back in time? We have to go back in time by x by v, because it takes x by v time to reach, for the message to reach. Now let us talk about that. Do we know what is the displacement of the particle at x is equal to 0? We know it, na? We know it. Y is equal to a sine omega t. Okay. So displacement of particle at x at time t is going to be, come on, let's go. It is displacement of the particle at x is equal to 0 at this time. So in this equation, we have to put this time. So what is the time? Time is t minus x by v is what we have to put here. So a sine omega into t minus x by v time we have to put, which is going to be what? A sine omega t minus omega by v into x is the displacement. Now look, what is omega? Omega is 2 pi by capital T. What is v? Lambda by capital T. Omega by v is 2 pi by lambda, and we define it with a new constant called as k, called as angular wave number. Called as angular wave number. So this can be written as what? Y is equal to a sine omega t minus kx. Now you tell me one thing, man. Is it mandatory that always the particle always this particle to be taken up only first? Is it mandatory that we have to take that up all the time? No, right? Might be we can take it down also. So if we take it down, if particle at x is equal to 0 is taken down, if it is taken down, then we should take it as minus a sine omega t. Then the same story, man. So instead of this, you have to put minus. You would have got minus a sine omega t minus kx. Y is equal to then a sine kx minus omega t. Now did you understand when to take omega t minus kx, when to take kx minus omega t? You have to choose kx minus omega t if the particle at x is equal to 0, at time t is equal to 0, is trying to move down. If the particle at x is equal to 0, t is equal to 0, if it is moving up, then you have to choose this. This is one big conceptual problem many people have. Many people have. Bharadwaj V, I'll check it, man. Let's first concentrate on this. There is no need for you to worry whether the JEE mains date have released or not. Okay. Now look. Hope everyone are clear. Now look, man. These are what? These are the equations for a wave traveling in positive x direction. For a wave traveling in positive x direction, where was that simulation? Okay, fine. I hope every one of you remember that simulation. So I would like to give one generalized expression, man. That is, one observation which I got is that when y is going to be a sine omega t minus kx, or when y is going to be a sine kx minus omega t, these are both what? Waves traveling in positive x direction. So I have a shortcut for this. I have a shortcut for this. The shortcut is going to be, man, you see the coefficient of x, you see the coefficient of x, you see the coefficient of t. If both of them have opposite sign, then it's a wave traveling in positive x direction. If coefficient of t and x have opposite sign, then it's a wave traveling in positive x direction. So that's it, man. Not only here, you can use it wherever you want. Not only here, you can use it wherever you want. Wherever you want. Okay, fine. Sir, is it mandatory that the wave should always travel in positive x direction only? What if they have given instead of x, z? Then instead of x, if they give z, it's a wave traveling in positive z direction. Okay. Now, sir, is it mandatory that it should travel only in positive x direction? Can't it travel in negative x direction? Yes, it can travel. Then how do we do it, sir? Then the wave is going to look like this, Sirji. Right? So, in this situation, let us say, for example, this is going to be the particle which is at x is equal to 0. That's the particle. Now, let us take one more particle which is having a displacement of y, which is at x distance at time t. So the same story, but the thing is, as the wave is traveling in this direction, now whatever the displacement this particle is having at time t will be the displacement of the particle at x is equal to 0 after some time. Why? Disturbance is now traveling like this. This is how the wave is moving. So first the wave will reach this particle, then it will reach this particle. So now these are previous particles. The wave reaches these particles first, then these particles. So I can say confidently now that displacement of particle at x at time t is going to be displacement of particle at x is equal to 0 at time t plus x by v. Because what are the displacement this one is having, this one will have after x by v time, because message takes time to travel. And the displacement at x is equal to 0 particle. Displacement at x is equal to 0 particle is what? Y is equal to a sin omega t, right? So a sin, if that particle is going to go first up, then a sin omega t. If it is going to first go down, then minus a sin omega t. So a sin omega into what is the time? T plus x by v. Man, we are getting the same thing, but both of them have same sign. So in the same way, I don't want to do the next one also. If you put minus a sin omega t for this particle, that means it is going down first. Then you get minus a sin omega t minus kx. So I'll simply write it like this now. If y is going to be a sin omega t plus kx, and if y is going to be a sin minus omega t minus kx. Minus a I should take, but that minus I have taken into the sign. Both these things are waves traveling in positive x direction. Both of them are waves traveling in positive x direction. And how to identify? See, thing is, here it's easy to identify, I have derived them, but there in future you are going to come across waves of different functions, not sine, not cos, something else. So for those things I am giving you shortcut. The shortcut is going to be if coefficient of x and t have same sign, then it's a wave traveling in negative x direction. It's a wave traveling in negative x direction. See the beauty. This is something which will not be understood by many students. So if you have to have confidence on waves, you should have clear understanding of what is happening everywhere. Everywhere. You should be able to feel it. Otherwise, waves will remain and will be difficult forever. Right? This is how I got grip on waves. Visualization, those simulations, whatever I have shown to you. Okay, fine. Now look. Man, let's say, let us just take this. Y is equal to a sine omega t minus kx. Now what I'll do is, I'll talk about dou y by dou t. What does this give you? Rate of change of position of particle, or you can say rate of change of displacement of the particle from the mean position. It will give you what? It will give you velocity. Okay, fine. Velocity of what? This gives you velocity of particle. Velocity of the particle. So what it will come out to be? I think a differentiation of sine will be cos, omega t differentiation will be omega. So I'm directly writing a omega cos omega t plus kx. And one more thing is that cos can be written as under root of 1 minus sine square. So velocity of the particle is going to be a omega under root of 1 minus sine square. Man, does it ring any bells? Isn't it looking like just an SHM thingy? Only thing is now, instead of displacement, there we have taken displacement to be x, but here displacement is in the y direction. So displacement instead of x, we are going to put it as what? Y. So when you simplify, you get it to be a omega under root of, sorry, not a omega, omega under root of a square minus y square. This I could have said to you without even solving it. Without even solving it, I could have directly given you this. Because anyway, I said that sinusoidal waves are produced by those particles which are going to be executing SHM. I said that to you. Okay. Now look. I am not going to be deriving rest of the things. So whenever they talk about the particle, it is SHM. Whatever we have learned in SHM are valid here. So what is the maximum speed of the particle? The maximum speed of the particle is going to be how much? Obviously a omega. When is that? When y is going to be 0. Okay man, I got dou y by dou t, right? Now I want dou square y by dou t square. Dou square y by dou t square. Then what is that you are going to get? Dou square y by dou t square is going to be what? Minus a omega square sine omega t plus kx. Just keep this in mind. I'm going to use this. Anyway, this is also going to be called as acceleration, but I'm going to use this for something else. Okay. Now look. This is the wave equation, right? So let me write that. Y is equal to a sine omega t plus kx. Now I want dou y by dou t. Dou y by dou t. Oh, dou t is already done, right? Dou x. A. Okay, now we are differentiating with respect to x. Sine will be cos, kx will be k, differentiation part. So ak cos omega t plus kx. And then when I differentiate it again, then what I get? A k square minus sine omega t plus kx. Now, man, tell me what is dou square y by dou t square divided by dou square y by dou x square. Look, here we have minus a sine and omega square. Here we have minus a sine k square. So minus a sine will get cancelled out. Are you going to get omega square by k square? And for your kind information, what was omega by k, sir? From here, can I also write omega by k as v, which is wave speed? Right? So man, this is wave speed. That means I can write dou square y by dou t square as wave speed square into dou square y by dou x square. This is called as differential form of wave equation. Although I derived it using the sinusoidal wave, but this is a wave equation and this is called as differential form of wave equation. Differential form of wave equation. And I keep my words when I give them. Do you remember? I said that wave speed is coefficient of t by coefficient of x. Do you remember that? See, wave speed came out to be omega by k. What is omega? Isn't it coefficient of t? What is k? Isn't it coefficient of x? I said I'll prove it in future. I proved it. So from now on, if you see not only sinusoidal waves, any wave you see, coefficient of t divided by coefficient of x is wave speed. That's it. Okay. Now, let us do this question. Whatever we have learned, let's try using this. Man, if you can visualize what is happening in front of you, nothing is going to be difficult. Nothing is going to be difficult. Keep that in mind. Now, the equation of a wave is y is equal to 0.05 sine. Okay. Find wavelength, frequency, and the wave velocity. Man, if you talk about wavelength, we can get it from k. That can be written as y can be written as 0.05 into sine pi by 2 10x, right, which is going to be what, 5 pi x, and then pi by 2 multiplied to that is minus 20 pi t minus pi by 4. And one more thing which I forgot to give, but I have given it in SHM. This whole thing is going to be called as phase, man. Because if you know this, then you know the displacement of the particle, like you know the position of the particle. So this whole thing is going to be called as phase, right? That is one thing which I missed to give. And one more thing is that, just a second. So that's going to be called as phase. Phase is what? Omega t plus kx. Now, if I want the phase difference, with respect to different particles, then differentiate d phi omega t 0. I am not changing time. I am looking at different particles at the same time, and it is going to be k into dx. So the phase difference can be written as k times the path difference. So the phase difference is going to be 2 pi by lambda into path difference. What is that path difference? We are talking about 2 points which are at different locations. So this is the first one which is at some x1, and this is the second one which is at some x2. So if you talk about the phase difference between these 2 points, it is going to be given by this. So how much length you have to travel means you have to travel x2 length or x2 path to reach this particle. You have to travel x1 path to reach this particle. This is one important result which you people have to keep in mind. Okay, fine. Now look. Wavelength. Man, this is k, right? So k is going to be how much? 5 pi. And what is k? It is 2 pi by lambda. So done. So lambda is going to be how much? 2 by 5, which is going to be what? 0.4 meters. Done. Frequency. Man, we have omega. Omega is going to be the thing which is multiplied to t. Okay, frequency is what? Omega by 2 pi, which is going to be how much? 20 pi divided by 2 pi, which is going to be how much? 10. And then they are talking about wave velocity. What is wave velocity? Wave velocity is going to be coefficient of t divided by coefficient of x magnitudes. Coefficient of t is how much? 20 pi. Coefficient of x is how much? 5 pi. So what is the wave speed? Obviously 4 meters per second. Okay, so the wave is traveling at a speed of 4 meters per second. Every second it will cover 4 meters. Super good. Now, particle velocity and acceleration at x is equal to 0.5 and t is equal to 0.05. See man, wave speed is different, particle speed is different. If you want to get the particle velocity and particle acceleration, particle is executing SHM, right? As the particle is executing SHM, we can write the velocity of it to be omega under root of a square minus y square, and acceleration is going to be what? Minus omega square y. Put the y value. So how do I get the y value? You have to put x as 0.5, that means half. So this is 5 pi by 2, right? So y is going to be 0.05 into sine 5 pi by 2 minus 20 pi into t, which is 0.05. 0.05 into 20, 0.52. So you will get minus pi. And then you have minus pi by 4. So what will be this whole angle, man? You can write it as 10 pi by 4, or you can say this is 2.5, right? So this will be 3 pi by 2, 3 pi by 2 minus pi by 4. 3 pi by 2 minus 5 by 4, right? So from there you will get the sine value. Once you get the sine value, you get the y value. Once you get the y value, you have to put the y value here. And you have to put the y value here. From there you will get the speed as well as acceleration. That's it. Speed as well as acceleration. So this part is like SHM, same like SHM. Same like SHM. So we don't need to waste time on this. Next. Okay. I taught you this. You people can answer. You people can answer it easily now. A transverse wave is traveling along a string from left to right. Okay. The figure represents the shape of the string snapshot at a given instant. At this instant, which points have upward velocity, man? See, the velocity will depend on the previous particles. What are the previous particles? The particles which have got the wave first. Okay. How it is moving? Left to right. So mark that it's a wave traveling in positive x direction. That means the previous particles. For example, if I am going to talk about the marked points A, B, C, D, E, F, G, H, right? Extend this wave thingy. Extend this wave. They haven't drawn the previous ones. Extend like this. Now look. This is A. This is B. This is C. This is D. This is E, F, G, H. Now for A, if you look at the previous particle, how is the previous particle for A? The previous particle for A is downwards. So the A has to move down. The previous particle for B is also down. The previous particle for C is also down. The previous particle for D is up. The previous particle for E is up. The previous particle for F is up. The previous particle for G is up. The previous particle for H is down. Now tell me, what are all the things having velocity up? D, E, F, G. Upward are going to be D, E, F, G. Okay. Hi Radhakrishna 143. Okay, fine. Now look. Which points will have downward velocity? How many? A, B, C, and H. So downward is going to be what? A, B, C, F. Okay, fine, good. Now, so if I'm going to talk about this, next is what? Which points have zero velocity? See, zero velocity are the ones which are going to be at extreme, right? So can I say the zero velocity to be the points which are at C and the point which is at G? Okay. Which points have maximum magnitude of velocity? Those are the points which are at the mean position. Max velocity. The max velocity is going to be those points which are at the mean position, which is A and E. Now I will extend this question. Which particles have downward acceleration? Which particles have upward accelerations? I am extending this question. This is A. This is B. This is C. And this is D. This is E. This is F. This is G. This is H. Which have upward and downward. Man, for all of these particles, this is going to be the mean position line. So A is on the mean position itself. So acceleration will be zero because at mean position force will be zero. Always force will be towards the mean position, so acceleration also should be towards the mean position. That means B should have its acceleration down, C should have its acceleration down, D should have its acceleration down, F should have its acceleration up, G should have its acceleration up, H should have its acceleration up. Acceleration will always be towards the mean position. No man, much of a class is not missed. People can watch through the recordings also. This is JEE Advanced 2000, sorry, IIT JEE 2008 question. Man, the reason why I picked this question is that if you use your common sense without solving, you'll get the answer. Look at the options. When these kind of questions are going to come, first look at the options. First option has direction as plus J. Next option has direction as minus J. And third option has direction as plus I. And fourth option has minus I. All the four options have different direction or not. That means if you are able to identify direction, you got the answer, right? Right or wrong? If you are able to identify, that's more than enough. Okay. Now, what is this? It's a wave traveling in positive x direction. They only mentioned it. It's a wave traveling in positive x direction. Okay, nice. Now, if you look at the point P, the previous particle to it is going to be this one. As the previous particle is up, so this particle should have velocity up. So that means it should have velocity in plus J direction. We have only one option, sir. Option A. That's it. Done. But you people don't leave it here. My request to you is that you just get the exact magnitude also. Entire data is given. You can calculate the magnitude. You can use V is equal to omega under root of A square minus Y square. For that, you have to calculate the displacement of the point P, right, from the mean position. Data is given. You can easily find it out. Data is given. You can easily find it out. Okay. Now, look at this question. This is 2022 You can see over here 2022 online 26th July evening shift. It's a JEE mains question. And 2020, 2021, 2022 are decent papers. 2023, 2024 are waste papers. Okay. A transverse wave is represented by y is equal to 2 sine omega t minus kx centimeter. The value of wavelength in centimeter for which the wave velocity becomes equal to the maximum particle velocity. Man, see, they are talking about what? They are talking about particle and wave. So they are saying both of them should be equal. Wave speed should be equal to a omega, it seems. Because maximum particle speed, this is max particle speed. They only gave it. I didn't take it, they only gave it. Okay. Now, the wave speed is going to be automatically omega by k, right? And what they're asking? Wavelength. So wave speed, omega by k is a omega. Omega gets cancelled out. Then the k is 1 by a. 1 by a. What is the amplitude? 2 centimeter. Right? So we can talk about 2 pi by lambda is going to be 1 by 2 centimeter. So the lambda is going to be 4 pi centimeter. Which option? Option A. Very good, Karthik. Now, one more. 2022 only. 2022 only. A longitudinal wave is represented. And one more thing, man. Whether it is a transverse wave or whether it is a longitudinal wave, same theory holds good. Only thing is that in your mind, transverse wave means displacement will be in the vertical direction. Longitudinal wave means it will be in the horizontal direction. Rest all are same. Rest all are same. Longitudinal wave is represented by this. So they shouldn't have used same x for both of them. You'll get confused. You take one to be capital X. So 10 sine 2 pi nt minus x by lambda, the maximum particle velocity will be 4 times the wave velocity if the determined value of wavelength is equal to. Same story da. A omega is equal to what? 4 times the wave velocity, which is omega by k. Ding. So k is going to be what? K is going to be 4 by a. So 2 pi by lambda is going to be what? 4 by a. So the lambda is going to be what? Pi a by 2. Pi a by 2. That's it. Let us not waste too much time on this. One more thing. In the beginning, I said that I'll prove that a traveling wave is going to have x and t in the same argument. I already proved, but I forgot to mention that. A traveling wave is one such thing which is going to have both x as well as t in the same argument. Same argument of the function, right? So I forgot. I proved it. If you remember, a sin omega t minus kx minus omega t. I proved it, but I forgot to give that statement. A sound wave of frequency 245 Hz travels with a speed of 300 along the positive x-axis. So all of them have quotient of t and x in the opposite direction. So that's of no use. Each point of the wave moves to and fro through a total distance of 6 centimeter. See, here their intention of to and fro about a point is going to be, that is this and this, not this as well as this, not this total thing. This and this is given as 6 centimeter. Then the amplitude is going to be what? 6 centimeter divided by 2, which is going to be how much? 0.03 meters, because it will be 3 centimeters. So which option has 3? See, we have to choose between these two, right? Now they have same k, they have different omega. So they have given frequency. Frequency is going to be what? Omega by 2 pi. And they gave the frequency as what? 245. So 245 into 2 pi is going to be what? Omega. 22 by 7. So 245 into 2 into 22 by 7 is going to be the omega value. So 245 into 2 into 22 divided by 7, which is 1540. Which is 1540 is omega. So you can say 1.54 into 10 to the power 3. So I'll go with this option. Okay, I already gave you the general equation of wave motion, man. When the paper has to be tough, they are going to frame questions on these things because most of the people have sinusoidal waves in their mind. Right? Sinusoidal waves are not the only waves that are present. There are many other forms of waves. So how do we identify when a form is given to us whether it's a wave or not? Look, differential form of wave equation is this. A wave should satisfy the above differential equation, and if a function is going to just satisfy this, that's not enough. You can't call it as a wave just because it is going to be satisfying this. There will be many functions which will satisfy this, but they will not be waves. What is the end condition? And should have finite values of displacement. Finite values of displacement. Example, sir. I didn't get you, sir. Example, when I say y is equal to 1 by 2x plus 3t. If you put it over here, might be it will be satisfying. Not might be, it will satisfy. But at the time t is equal to 0 and for particle at x is equal to 0, what is the displacement of the particle which is at x is equal to 0 at time t is equal to 0? Infinity, man. So how come a particle go to infinity? Can it ever reach infinity? And how come a particle which is oscillating have infinite amplitude? Not possible. So we can say y is equal to 1 by 2x plus 3t is not a wave. Although it is going to satisfy the differential form of the wave equation, this is not going to be treated as a wave. Reason being, it has infinite displacement from mean position, which is nonsense. Nonsense. I mean it. Okay. Now, sir, then what should we do? Should we verify whether it is going to satisfy the wave differential form of wave equation first, or should we verify whether it has finite values? My suggestion to you is that you first verify whether it has finite value or not. First what you have to do? First verify whether y is finite or not while solving questions, rather than verifying whether it is going to be obeying the differential form of wave equation or not. Okay, now let us talk about this question. Right? And one more thing, man. They gave a transverse displacement wave on a string is given by, I think the letters are too small, I'm writing it, y of x comma t is going to be what? E power minus ax square plus bt square plus 2 root ab xt. The initial impression on this is going to be like, what nonsense is this? How come x square t squares are there? Till now we have discussed about having x and t. What are these things? Man, if you observe properly, it is root ax plus root bt whole square. So in the same argument, do you have both x and t or not? Yes, we have it. Yes, we definitely have it. So this should be, if it is a wave, it should be a traveling wave. If it is a wave, it should be a traveling wave. And it's a traveling wave in which direction? Negative x direction. Why? Coefficient of x, coefficient of t are positive. Same sign. They have same sign. What to do? Okay. Now I have to see whether the values are finite or not. Don't look at the options. I am not bothered about options. First, let me check whether it's a wave or not. So when I put x is equal to 0, t is equal to 0, I get 1, e power 0, 1. If I put x as infinity and t as infinity, any one of them as infinity if I keep, then e power minus infinity will be what? 0. So if you talk about the range of this function is between 0 and 1. So finite values or not. So mostly if it is a finite value having x and t, then it's mostly a wave, right? Okay, it's a wave, right? And what will be the wave speed? It's a traveling wave in negative x direction. So this option is ruled out. Standing wave is ruled out. The only option left is this. But still I will go and calculate the wave speed. What did I define as wave speed? Wave speed is going to be coefficient of t divided by coefficient of x. What is the coefficient of t? Coefficient of t is root b. Coefficient of x is root a. So root b by root a. So option 4 is correct. Next, this is a good one. In recent times, I think 2021 or as far as I remember, similar question was asked in 2021 or something. Sadia Sultana, super. Okay. See, I'll be looking at the chat, but whenever it is needed, only then I'll speak out. Right now I have given a question, so you people have to try. Please try it. And man, I have a small request. See, in this English channel, we have people from many states, right? I don't like the live watching to be bit less. I get a lot of motivation when there is huge number of people watching it live. I don't know, for some reason I get a lot of energy. So I have only one request. For me to be energized and give all the good content, whatever is there, we have only one small request. Not one, make it 2. The first one, please smash that like button, whatever is there. Automatically YouTube algorithm is going to take this video to many people, right? Second, you will have your friends in the school, right? You suggest them these videos if you feel that they are worthy. We are not asking you to suggest if you feel that they are not worthy. If they are worthy, suggest them. Then one good thing is going to be you and your friends are going to be watching the same video. Then you people can discuss the concepts among yourselves. When you discuss with people, that's when the concepts are going to become stronger. So the next class is also going to be on waves. I'll be completing waves tomorrow. So before your Diwali, I'll be completing the waves. Okay. Now, disturbance of a wave propagating in the positive x direction is given by, okay, at time t is equal to 0. This is the problem. And propagating. It's propagating. That means it's a traveling wave. Okay. When you put t is equal to 0, then automatically that t gets kicked out. And you can see that there is x minus 1 has come when t is going to be or 2. So it's a clear thing that the equation has 1 plus x some plus bt square you take. As it's a wave traveling in positive x direction, coefficient of t and coefficient of x have to be opposite. So I'll take it like this. It's a wave traveling in positive x direction. Okay, I'll take, as x is having coefficient as 1, I'm taking coefficient of t to be b, in fact minus 1. Now, at the time t is equal to 2 seconds, what will be the wave equation? Y by 1 plus x minus 2t whole square. Oh, not 2t, b into t. So what do you get? What do you get from here? You get y to be 1 by 1 plus x minus 2b whole square. So compare it with this. So 2b is what? 1, right? So if you compare, 2b is 1, so the b is half. Now what are they asking? They are asking the wave velocity. See, I got the b to be half. Then what will be the wave equation, sir? The wave equation is going to be 1 by 1 plus x minus t by 2 square. So from here, what is coefficient of t? Half. Like magnitude of coefficient of t? Half. And what is coefficient of x? 1. So what will be the wave speed? Simply it is going to be half by 1, which is going to be half, which is going to be 0.5. So the answer is going to be 1. So these are the kind of questions you are going to get if it is not going to be a sinusoidal one. If it is not going to be a sinusoidal one. See, now, intensity of the wave. Yep, very important. But ultimately the formula is important, not the whole content. Man, what is a wave? Wave is a disturbance which is going to carry energy from one place to the other place. That's what I have here. Wave is a disturbance which carries energy from one place to other place. So, who is supplying energy to it? If you remember, there was one thing which was taking the particle up and down. There was one rod and there was a circular disc. That disc was rotating, then the rod was moving up and down, and that rod was the one which was giving energy to the particle, and that energy is getting transferred. Right? So, what is intensity defined as? We have already seen the intensity in the previous classes also, right? So, what is intensity? Intensity is going to be rate of flow of energy per unit area. So the intensity can be simply written as power that is going to be crossing per unit area. Power that is going to be crossing per unit area. Okay. And if we talk about power, the power is going to be the force times the velocity. And if I am going to talk about a wave, how is a wave? Look, let us talk about some situation like this. So, this particle has some velocity v like this. Obviously, the one as the surrounding particles will be applying some T force like this, whatever the work will be done against its willingness, some external agent. Let's say with my own hand, I am applying force like this. So whatever the force I apply directly on the string will be the tension in the string. So the tension will be like this, then the force I have applied is going to be like this, then this is the angle. So instantaneous power, the instantaneous power I have delivered is the force I have applied at that instant multiplied with velocity of the particle, because I am giving energy to that particle and the particle is giving energy to the next one, and then the next is going to give to the next, and then the energy is going to flow. So when I calculate the average power that is going to be given in one time period, it is half mu a square omega square into v, where this v is wave speed. So if someone is going to ask you averagely how much energy has been sent in one time period, average energy that has been sent in one time period, it is the average power multiplied with the time period of one oscillation. Now if I am going to talk about the average intensity, it is going to be the average power that is going to go through divided by the area of cross section of that material in which you are sending the power. So obviously whatever I am going to send, it is going to be through a rope, right? Through a string, whatever it is, and that string has some cross sectional area. So the cross sectional area, let us take it to be A, and we are feeding the power, and the power is going to go, or the energy is going to go through the strings like this. Energy is going to go through the string. Okay, then how much is that intensity? Half mu a square omega square into v divided by the area. 1 second, this cross sectional area, whatever is there, I'll take it as S. I will take it as S because A is taken already for amplitude. Now tell me, mu is mass per unit length. Mu is mass per unit length. Mu is mass per unit length. Okay. Now mass per unit length per unit area. Mass per unit length per unit area is nothing but mass per unit volume or not. So I can write this section. I can write this section as rho, and I can write it as half rho a square omega square into v is the intensity, and this is the formula which you can use for any wave you come across. Any wave you come across. Okay. Okay. Now, there is one common misconception with many students, man. That is, intensity of a wave is directly proportional to amplitude square. Wrong. Why? This is not valid. Not valid all the time. Not valid all the time. This is not valid all the time. Okay. Sir, I didn't get you, sir. Man, if you are comparing two waves traveling in same medium, wave speed will depend on medium. It has nothing to do with the source who has created. Keep in mind, wave speed depends only on the medium in which it travels. Frequency depends only on source but not medium. How fast I speak, the number of words I speak. I can speak very slow. I can speak very fast. So the frequency of words depends on my mouth. But once they go out into the surroundings, the speed with which they travel is 330 meters per second in air. Whether I speak very slowly, whether I speak very fast, even then, the speed with which the wave is going to travel has nothing to do with my mouth. It has everything to do with the medium. A very important thing. Now, if someone is going to say this, man, intensity is half rho A square omega square V. We can say I is proportional to A square only when we deal with waves having same frequency and traveling in same medium otherwise you can't. Why? If I say same medium, then density of the medium and V is going to be same, right? And when I say same frequency, then omega is also same. That means rho half omega square half rho omega square V are constant. Then those constants can be replaced with a proportionality. So intensity is proportional to amplitude square. If waves travel only in same medium but their frequencies are not same, in that case the intensity will be proportional to amplitude square as well as omega square. The important thing, can test your knowledge, can test your understanding. Okay, now let us go. We are done with energy. We are done with the basic wave speeds from the wave equations. Basic speed from the wave equations. Okay, Jahnavi is asking, sir, when will you do AC? I'll do, I think, I'll do if it is not already done. I'll do if it is not already done. Okay, fine. Let us continue. See, what we have done till now is that, okay, there is a power cut. Can you people hear me? Can you confirm once? Can you people hear me? There is a power cut. Type in clear. Type in clear. Please once type in clear. Type in clear. Please type in clear. I'll continue. Okay, fine. We will go ahead. We have done energy, intensity. We have done in general, if a wave equation is going to be given, how do we find the speed and all that stuff. Now specifically we will talk about transverse waves. So if we have a string which is maintained under some tension, so let us take tension in this string, in that section of the string is T, and one more thing is mu, which is mass per unit length. So I am not going to derive this, wasting time. Those who are interested, derivation is there in H.C. Verma also, right? Now, what will be the speed of a transverse wave in a string? It is under root T by mu. Just mug it up. The derivation is not worthy. Not needed at this point of time. Although those who are interested, we have the derivation in H.C. Verma, you can go for it. So speed of a transverse wave in a string is going to be given by under root T by mu, where T is tension, mu is mass per unit length. T is tension and mu is mass per unit length. Okay, fine. Now, just a second. Okay. Speed of a transverse wave on a string. Let us see. And one more thing, I don't know why. Basic questions they ask on speed of transverse wave. Basic questions. Speed of a transverse wave on a straight wire. They gave mass, they gave length, they gave area of cross section. We don't need area of cross section. Is 90 meters per second. If the Young's modulus of the wire, now we might need it. The Young's modulus of the wire is 16 into 10 to the power 11 Newton per meter square. The extension of the wire over its natural length. Man, speed of a transverse wave is given by root T by mu, where V is how much? 90. Root T by, what is the mu value of 6 grams, which is 6 into 10 to the power minus 3, divided by 60 centimeters, 60 into 10 to the power minus 2. So, 90 equal to, now 90 meters per second, right? 90 square is going to be 90 into 90 is T by, what do we have? We have 10 to the power minus 2 or not? Because 6 gets cancelled out, you have 10 to the power minus 2. So the tension is 81 Newton, man, right? So the string is under a tension of 80 Newton. String is under a tension of 80 Newton. Okay. Now look. So let us take that string. Let us take the string and it is pulled from both the sides with a T. The Young's modulus, we know it to be what? Stress divided by strain. So what is the stress now? Restoring force developed. At equilibrium, restoring force developed will be equal to the force we are applying, which is going to be T divided by A. They are asking you what? Extension. So extension by the original length. Young's modulus they gave. So Young's modulus is going to be T into L by AE. So the extension can be written as what? T into L by AY. I am leaving the calculation part to you. Okay. Now, a transverse wave travels on a taut steel wire. Taut means the one which is having tension in it, like tight one. A transverse wave travels on a taut steel wire with a velocity v when the tension in it is 2.06 into 10 to the power 4. When the tension is changed to T, the velocity changes to V by 2. The value of T is close to, man, V is going to be what? Root T by mu. If you are talking about the same string, then the speed is going to be, speed square will be proportional to the tension. So we can say T1 by T2 is going to be V1 by V2 square. T1 is how much? 2.06 into 10 to the power 4. T2 we don't know, but what happened to the velocity? It became half. So V1 by 2, or we can say V1 is V, V2 is V by 2, which will become 2 square. Then T2 is going to be what? 2.06 into 10 to the power 4 divided by 4. So 2.06 divided by 4 will be how much? We should have 10 to the power 3. We should have 10 to the power 3. 2.06 divided by 4 is going to be 0.515 into 10 to the power 4. So 5.15 into 10 to the power 3. Okay. Next. This is one good question which involves a bit of integration. Why? See, even these kind of questions should be there on your fingertips. I'll just do it. Reason is, majority of the questions are going to have constant tension throughout the string. Majority of questions will have constant tension throughout. But sometimes the questions are not going to have constant tension throughout. Sometimes we won't have. For example, let us take a situation where there is a rope which is going to be hanging like this. A rope which is going to be hanging like this. Okay. Now, I create a disturbance here, and let us take the mass of the rope to be m, length to be l, right? And the mass per unit length, you can take it to be mu. That mu is going to be how much? M by L. What I do is I'll create a small disturbance. I'll hold here and I'll just give a jerk. I will hold here, I'll just give a jerk. Then when I give a jerk, that jerk is going to go up or not. How much time it takes to go up is the question. Now here we have a problem. Tension throughout the rope is not same. Tension throughout the rope is not same. Why? I'll show you. For example, if I am going to talk about an element or a strip of mass, a layer of mass at x distance, that layer of mass should balance out the whole weight of this. What is the weight of this section? Total mass is m. In how much length? L length. So m by L is mass per unit length into x. So if I draw only this section separately, that section is in equilibrium or not. It's not going anywhere. Now, if you talk about the forces acting on it, the forces acting on it is gravitational force, which is going to be m by L into x is the mass into g. Now, that green layer is also going to apply force, right? So whatever the force the green layer is going to be applying, let me call it as tensional force. Obviously, one layer applying force on the other layer is nothing but the tensional force in the string or in the rope. Okay. Now you tell me, as the net force is going to be 0, what is the tensional force? Can I say m into g into x divided by L? So what is happening? If you go to different x values, the tension is different. That's the problem. So depending on the tension only, wave speed will depend, na? Wave speed is what? Wave speed is root t by mu. And if you observe this properly, m by L is mu only, na? So then it is going to be mu into g into x divided by mu. So the v is going to be what? Root gx. So the wave speed is also continuously changing. Wave speed is continuously changing. So how do I calculate how much time a disturbance created at the bottom will reach the top? How do I do that? Now look. Let us draw the same diagram. Let us do the same thing once again, and let us have a deep look at it. At a distance x, let us talk about dx length. Dx is very small distance. So as it is very small distance, more or less the tension in that entire distance will be same. So whatever the disturbance I created will be traveling this in how much time? It is going to be distance divided by the speed. Dx distance, it is traveling with v speed. Why I said v speed? Because more or less this distance is very small, so you can treat it as one single layer, and the speed at that single layer is going to be given by root gx. Okay, I know majority of the people don't like integration, but it is not a difficult thingy. You look at it and you get it. See, 1 by root g, I'll take it out, and this section is x to the power minus 1 by 2 into dx, man. Now, see, to to travel this dx distance, it is taking dt. Like that, it has to travel here, 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 here. So if I calculate all the times it has taken to travel all these small distances, and if I add them up, how much time it took to travel this distance, then this distance, this distance, this distance, like that, if I calculate all those small times and if I add them, I'll get the total time it has taken to travel the entire length, right? So adding up is what? Integration. Then 1 by root g is a constant, so I have taken it out directly. From where to where? You are talking about x. You have taken x from here. You have to go till here. So your x here is going to be 0. And here x is going to be what? L. 0 to L. So the time it takes is going to be 1 by root g. X to the power minus 1 by 2 is going to be what? X to the power minus 1 by 2 plus 1 by minus 1 by 2 plus 1. Which is going to be this. Is going to be what? 0 to L. Now you put the limits. So the time is going to come out to be what? The time is going to come out to be 1 by root g, right? If you put the limits, it's 2 times root L. So the time it takes is 2 times root L by g. This is a question sometimes directly asked in many of the competitive examinations. Like if you talk about the second layer of examinations like VAT, BITS and all those things, huh? Yes, these things are going to be, this is going to be helpful. So the time is going to be 2 times root L by g. So if I hold on to this rope here, if I give a slight disturbance, the disturbance will be traveling on this rope and it will reach the top of the rope in this much amount of time. Okay. Now, is it mandatory that we should have only one wave traveling in the medium? No, not at all. Never. We can have multiple waves traveling. For example, when I talk, you see, assume that you people are there in a classroom. All of them start talking at the same time. Then you have multiple waves in the same medium, right? Then you have multiple waves in the same medium. Then how the particles are going to be behaving? It is given by principle of superposition. What is that? If 2 or more waves arrive at a point simultaneously, then the net displacement at that point is the algebraic sum of the displacement due to individual waves. You just take one wave, how much it is going to displace, then keep it aside. Then you take the second wave, how much it is going to displace. You take the third wave, how much it is going to displace. Add them with proper sign. That's what you get. Add them with proper sign, you get the overall displacement. That's it. And one more thing, they cross each other. Waves cross each other without affecting each other. Without affecting each other. They just cross. That's it. Okay. Now, take this question. It's a good way to visualize. It's a good way to visualize principle of superposition. After this question, I'll give you some 10 minutes of break and then I will start again. We have to complete up to standing waves. So I have to do reflection of waves, right? I have to do reflection of waves and then standing waves on string and then sonometer. So basically, we have around 1.5 hours of class left. 1.5 hours of class left. I'll go have some water and come back. Okay, come on. In the arrangement shown in figure, a rectangular pulse and a triangular pulse are approaching each other. The pulse speed is 0.5 centimeters per second. Sketch the resultant pulse at time t is equal to 2 seconds. Man, first of all, you just take this as your reference. That is going to be your x is equal to 0 thingy. Now in 2 seconds, how much this pulse will travel? That pulse, you just draw it separately. How much this will travel? It is traveling with 0.5 and traveling for 2 seconds. So this will cover 1. That means, see, this is your x is equal to 1, man. So the pulse, this rectangular pulse will be here. Now what about the triangular pulse? The triangular pulse, whatever is there, I will draw it with blue. So the triangular pulse is also traveling with how much speed? 0.5 only in this direction. So in 0.5 into 2, total how much it will travel? 1. That means it will just reach, okay. Let us draw it separately so that you will have better understanding. So where the pulse will reach the pulse, this left end will reach 0, this top will reach 1 because the top is at 1, sorry, the top is at 2 here. The top is at 2 here. So the distance between this left end and the top is going to be 1. So the top, left end will be here, and the top will be here, that is at x is equal to 1, and the other end is going to be at 2. So this is going to be x is equal to 1, this is going to be x is equal to 2, this is going to be x is equal to 0, and this is going to be x is equal to 1. Sketch the resultant pulse. If not, okay, sketching the resultant pulse, I will leave it to you. Just tell me what is the net displacement of the particle at x is equal to 1. Displacement of particle at x is equal to 1. Red wave is asking it to go up by 2 centimeters because they said, right, height is 2 centimeters. So the red one is asking it to go up by 2, and even the blue one is asking it to go up by 2. So it is going to be 2 plus 2, which is going to be 4 centimeters. Now let us talk about the particle which is at x is equal to 0. If you look at the x is equal to 0, red one is asking it to go up by 2, blue one has just reached, it is not asking it to go up. So it is going to be 2 plus 0, which is going to be how much? 2. If I am going to talk about the particle which is at x is equal to 2, x is equal to 2, did the red pulse reach x is equal to 2? No. And what about the blue pulse? Blue pulse is asking it to go up by 0 only because that is also at mean position. So it is 0 plus 0, which is going to be how much? 0. So the diagram of the pulse, I am leaving it to you. You spend more time, you get better visualization. You spend more time, you get better visualization. Right? Not a difficult one at all. Look, this is the section where two of the waves are affecting. So all the particles which are going to be between x is equal to 0 and x is equal to 1 have to respond to the blue wave as well as to the red wave. So the particles which are to the left of x is equal to 0, only red wave is there. The particles which are to the right of x is equal to 1, only blue wave is there. So you have to be careful with this. This plus this has to be done. So it will be a straight line with intercept. It will be a straight line with intercept. Okay? Okay. Now, man, what's the time now? My tongue is twisting. It's 7:40. It's 7:40 now, 7:40 p.m. We will meet exactly at 7:50 p.m. So, break for 10 minutes. We will meet at 7:50. Okay. Meanwhile, those who want to try this question, those people can keep trying this question and get the diagram. Just 10 minutes of break. I'll be back at 7:50. Can you hear me? Please say clear. Please say clear. If you can hear me, please say clear. If you can hear me, please say clear. Meanwhile, I have just gone through the notification the JEE mains has released, and the syllabus hasn't changed. So whatever the syllabus you had in 2024, it's the same syllabus in 2025 also. It's the same syllabus in 2025 also. So you people don't need to worry at all. So the reduced syllabus, whatever is there in 2024, it's the same syllabus now also. Okay. Please say clear, man. Please say clear fast. I have a doubt whether you people are able to hear me or not. One important update is that syllabus is same, and you have negative for numerical questions. Syllabus is same. So deleted syllabus, whatever is there in 2023, 2022 at that point, say I think 2023 only they are deleted. Same syllabus. Okay, Varshit. Okay, now we have to talk about interference of waves. We will talk very less about it over here, and we talk about it more in wave optics. So whatever I am going to do over here is just the basics of it. So what is interference? Now we are talking about 2 or more waves, right? So if we have 2 or more waves traveling in the same direction, having same frequency, if they are going to interfere with each other, then an interesting result is going to be appearing in front of our eyes. For example, if we have y1, which is some a1 sine omega t minus kx, and if we have y2, which is going to be a2 sine omega t minus kx plus theta, then the resultant displacement is going to be sum of the individual displacements as given by the principle of superposition. I have done phasor diagram to you in SHM. So when you have trigonometric functions, you don't need to blindly do the trigonometry. Okay. So what does all those things say? Let us blindly go with phasor diagram. What does the phasor diagram say? You draw a horizontal and you take any one of the phases as your reference. I'll take omega t minus kx as my reference. Right? Now, I have to draw a line which is going to be equal to the amplitude. So I have to draw A1. Now we have one more, right? What is that other one? Omega t minus kx plus theta. So the phase of it is omega t minus kx plus theta. And what is the amplitude? In that direction, it's A2. It is A2. So now we have to talk about the resultant of these two. So the resultant of these two is going to give us the resultant amplitude, which is going to be how much? Under root of A1 square plus A2 square plus 2A1 A2 cos theta, where theta is the angle between these two. Let us say that this green thingy, whatever the resultant is there, is making an angle phi. Then what will be the phase of the resultant? Omega t minus kx plus phi. So we can write the resultant one as resultant amplitude into sine omega t minus kx plus phi. Do we know the resultant? Yes. Now look, man. So the resultant amplitude is under root of A1 square plus A2 square plus 2A1 A2 cos theta. Let me do the squaring. If I do the squaring, AR square is going to be A1 square plus A2 square plus 2A1 A2 cos theta. For your kind information, do we know the intensity? Yes. We have the intensity formula to be half rho a square omega square into V. So instead of writing half rho omega square V, as all of it is going to be a constant, I'll simply write it with some K. Or if you are not interested, I'll write it with C. So C is what here? C is what here? C is going to be half rho omega square into V. Now you tell me, the resultant amplitude square can be written as resultant intensity by C. A1 square, I1 by C. I1 is the intensity of the first wave. A2 square, intensity of the second wave by C. So 2 times root I1 by C, root I2 by C into cos theta. So IR is going to be what? I1 plus I2 plus 2 root I1 I2 cos theta, a very important result which will be used in future, where majority of times this part of it will be covered in wave optics. Sir, where is Navamita ma'am? Which channel did she go? I don't know. She is not in Vedantu. She left Vedantu, right? Now look. Generally what our common sense is, I1 energy, I2 energy together should come out to be I1 plus I2. That's what our common sense is. We have two waves, man. Let us go back. We have two waves. The first wave has an energy intensity of I1. The second wave has an intensity of I2. If you club those two energies, our common sense says that it should be I1 plus I2. But interference says that no, it might not be I1 plus I2 all the time. It is this. That's why interference of waves is so famous. That's why more, yes, slightly more. Okay. That's why this is so famous. This is not just simple addition. It's coming beyond I1 plus I2. And sometimes it will be less than I1 plus I2 also. It's so weird to visualize that. Your clubbing energies and the resultant energy is not some of those energies. It's different. Okay. Now look, that's when people are going to talk about something called as constructive interference and destructive interference. Constructive and destructive interference. Man, if two things are going to meet in such a way that the output is maximum, we say that those two have done the work in a constructive way. For example, we have two people. We have assigned them to do the work, and the work has come out to be tremendously good. That's an indication that this person and this person have done it in a constructive way of approach. So if the resultant intensity is maximum, if the resultant intensity is going to be maximum, that's when we say that the waves have met in a constructive way. Now look, I1 and I2 are constant. The only thing is going to be cos theta. The way we mix the waves. I have taken two waves. Those two waves, how I mix them, depending on that I get the resultant intensity. So as I have taken two waves, intensity of the first wave is I1, intensity of the second wave is I2. So we won't change that. We will change the way we mix them. And what is theta? Phase difference. How I know? Look, what is the phase of the first wave? The phase of the first wave is omega t minus kx. What is the phase of the second wave? Omega t minus kx plus theta. So what is the phase difference? Theta. Okay. Now you use your common sense. This is constant, this is constant, this is constant. For this to be maximum, what should be cos theta? 1. So the cos theta should be 1. That means the theta should be 0 plus or minus 2 pi plus or minus 4 pi and so on. Right? Now look, that theta can be called as what? Phase difference. And I can write it as plus or minus 2n pi, where n is going to start from 0, 1, 2 and so on. So if the phase difference between the waves you are clubbing is going to be plus or minus 2n pi, then the output is maximum. Okay, sometimes they are going to ask you to answer it in terms of path difference. Phase difference is what? In this class only I have done it, 2 pi by lambda into path difference, which is plus or minus 2n pi. So 2 pi, 2 and pi gets cancelled out. So if the path difference is going to be plus or minus n lambda, integral multiples of lambda, then the waves will undergo constructive interference. When they undergo constructive interference, what is the advantage you are going to get? You get the intensity to be maximum. How much is that? How much is that? That resultant intensity is I1 plus I2 plus 2 root I1 I2 cos theta how much? 1. Cos theta how much? 1. So this can be written as what? The resultant intensity is maximum, and if you look at it, it is under root of I1 and it is under root of I2 square. Under root of I1 plus under root of I2 whole square. Okay. Now if I am going to talk about destructive interference, the resultant intensity should be what? Minimum. Now you only use your common sense and tell me, if cos theta is going to be put minus 1, only then this will be minimum, right? Because I1 is constant, I2 is constant, this is constant, cos theta has to be put minus 1. So cos theta has to be minus 1. Indicating what should be the values of theta, plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, and so on. So the phase difference can be written as plus or minus 2n plus 1 pi, where n is going to start from, 1 second, I will try to avoid this and I'll write 2n minus 1, where n starts from 1, 2 and so on. Why I am avoiding n is equal to 0, you will understand it in wave optics YDSC. You will understand in wave optics YDSC. Okay, now look, same thing, same story, 2 pi by lambda, path difference is plus or minus 2n minus 1 pi. So the path difference is going to come out to be 2n minus 1 into lambda by 2. 2n minus 1 is odd number, plus or minus. Odd multiples of lambda by 2, if you see, if the path difference between two waves is odd multiples of lambda by 2, then it will be destructive interference, and the resultant intensity is definitely minimum. How much is that? It is I1 plus I2 minus 2 root I1 I2, which can be written as root I1 minus root I2 whole square. Root I1 minus root I2 whole square. Okay, now reflection of waves. Before we go for reflection of waves, I would love to show you some animations. As usual, some simulations. Only simulations will make you understand what is happening. Again, we have come back to the simulation 1. Now look, reflection from fixed end, reflection from free end are two things which we are going to come across frequently. Reflection from fixed end and reflection from loose end are two things which we are going to see. Just a second, just a second. Okay, now look, let us play it. This, you can see I have selected something called as no end, right? Okay, 1 second. Now let me put fixed end, let me keep it normal. See, this point is fixed, it is fixed between the ends, and now you see what is happening over here. The behavior has changed. Let us restart it. The behavior has changed a lot. Look at this section and look at, once it is going to go over there. Look at this section and look at what is going to happen when it is going to go over there. Okay, you see, can you see visible changes in this portion, and this portion is behaving in one way and this portion is behaving in one way. You can't see what is happening, why that is happening. You can see some points to not move at all, and you can see some points to move maximum. Now let us do loose end. Let us do loose end. Loose end is nothing but you don't have rope on that side. No end means you have a rope which is infinitely long. Free end means you have no rope onto that side. And if it is a fixed end, it will be that particle whatever will be over there will be rigidly fixed. That means it can't move at all. Now look what will happen. Look at this motion and look at once it reaches the ring. The movement of this section is changing. Can you see that? Can you see that? Because in this section we have waves traveling in two directions, and in this section we have only one, and that reflected wave is continuously traveling. There is transmitted wave and there is reflected wave. Both of them are going to interfere and we get this kind of situation, and it is very hard to visualize this section. What is happening inside, we can't feel it. I have one more animation to show you what is happening inside. Da-dang. Look there, look everyone, I'm starting it. You can see I have selected from a fixed end. This is fixed end and I am sending a traveling wave. How I am going to send a traveling wave? I will be like oscillating it up and down, then there will be a traveling wave going on there. And those red dots you see, the dark dots, those dots are the particles of the medium. Those dots are the particles of the medium. Hi Shiv Kumar, come on. Now look, I'll put slow motion. Just look. Now this will ask this to go up. Now this starts going up. Then this will ask this to go up. Then when this starts going up, this will ask this to go up. When it is asked to go up, can it move? Can that particle move? No. So one wave is asking it to go up. And what is principle of superposition, man? Net displacement of the particle is sum of the individual displacements due to all the waves. I can see one wave. That wave is asking it to go up, but it is not able to go up. That's a clear indication that the wall, which is fixing that particle, should create one more wave in such a way that if this wave is asking it to go up, this wall should create one more wave which is asking it to go down by the same amount. By the same amount. Look. How much our red wave is crossing, that much blue wave is getting created. You can see when half of the red wave is going to be crossing, I will pause the video and look at the behavior. See, these particles, whatever are there, this one, this one, this one, and this one. So these four particles have to respond to the red wave which we have thrown, the incident wave, and should respond to the reflected wave also. That's why these particles' behavior is different when compared with these particles' behavior. Now, when half of the red wave is going to cross, you see, when half is going to cross, let me pause it. Yes. When half of the wave has crossed, half of the wave is produced by the wall, and this wave produced by the wall is what we call as reflected wave. So an upward pulse, whatever is going to go, is getting reflected back as what? Downward pulse. Now these particles have to respond to two waves. One which I created, which is sent onto this wall, and one which is created by the wall. So the one which I have created is red, the one wall has created is blue, and this red and blue will be inside the string. So this red and blue, whatever is there, is what is happening inside the string. And what you see in reality is the movement of the particles. Look how the particles are going to move. I'll remove the slow motion. Some particles are not moving at all. The particles which don't move at all are going to be called as nodes. And some of the particles are having maximum displacement, or you can say maximum amplitude. So those particles which are having maximum amplitude of oscillations, those are going to be called as antinodes. Then what about the particles in between, sir? they will have their amplitude of oscillations between 0 and between maximum amplitude. Look at this. It has an amplitude. Look at this. It has this much amplitude. And it will go up also by the same amount. Now, if you talk about this one, let us talk about this particle. You can see it is having this much amplitude, this one. So now what we have understood, when we make two equal and opposite waves travel in the same string, we will have some points which don't move at all. We will have some points which are going to move maximum, and we will have some points which are going to be having amplitude of oscillations between 0 and maximum. 0 and maximum. Okay. Now, few more interesting things. So I realized that all the particles are not going to have same amplitude. In traveling wave, all the particles will have same amplitude of oscillations. Second, can you see all the particles to be crossing the mean position at the same time? Let me show you. You look, all the particles are crossing the mean position at the same time. That doesn't happen. That doesn't happen. That doesn't happen in a traveling wave. So whatever we have got now, this is actually standing wave. So I am covering you the basic theory for standing wave also. Nodes, antinodes, nodes, antinodes, and all that stuff. So antinodes are those ones which are going to have maximum amplitude. Nodes are the ones which are not going to move at all. And when these things are going to get created, when you have two waves, two equal and opposite waves, and this is from fixed end. Now let us change it. Start. Now I have kept free end. I have kept the end to be free. Then what will happen? We have the wave which is being sent onto this medium, right? And that end is free. That end is free. Let's see what will happen when we are going to take it to that end. Man, one small thing which I would like to tell you is that if there are more and more particles onto that side, it is supposed to go up by A. But as there are no particles on that side, this is free, so this should actually go extra. When there are particles, those particles whichever are going to be on this side, they oppose the movement. So when this particle is opposed to move, if it is going to go to this side, when there are no particles, there is no opposition, it should overshoot. That's what I think. Let's see what physics is going to say or show us. Let us see. See, okay. I feel that it should overshoot. Yes, it is overshooting. Now again, principle of superposition is going to be like, array man, if it is overshooting, then definitely there should be one more wave. Yes, we have one more. Even the free end is able to reflect. Even the free end is able to reflect. If it is only the red wave, the particle should have gone up only by this much. But the particle is overshooting, clearly indicating that there is a wave created at the free end also. An upward pulse we have sent. Half of the pulse has crossed, half of the pulse got created. So upward pulse will be reflected back as upward pulse if it is a free end. Upward pulse will be reflected back as a downward pulse if it is a fixed end. Right? You can see what will happen in these situations also. I'll remove the slow motion to save time. What's happening here? Same situation. Some particles don't move at all. We call them as nodes. Some particles are moving maximum. We call them antinodes. Some particles are going to be having amplitude of oscillation between 0 and maximum. Yes. and all the particles are crossing the mean position at the same time, all of them are reaching their respective maximas also at the same time. All cross mean position at the same time, respective maximas also at the same time. I don't know whether you are able to see it or not. The particle at antinode crosses the mean position with maximum speed because its amplitude is big. And the maximum speed of a particle executing SHM is going to be given by amplitude times omega. If amplitude is maximum, obviously the speed with which it has to cross is also going to be what? Maximum. Okay. Now, let me show you here also. We'll talk about a pulse. You see what will happen. I'm sending an upward pulse. Oh, this is too slow. This is too slow. I will keep the tension high so that you people will be able to feel it. And I'll keep the amplitude also a bit high. Now look, man. Loose end, upward pulse is reflected back as what? Upward pulse. And this one is fixed now. So upward pulse is reflected back as what? Downward pulse. How much of the reflected gets produced? How much our incident crosses, that much reflected gets produced. Downward became upward. Upward, free end. Upward pulse only, it should get reflected back. See? Yes, upward pulse only. Now it is reaching to the fixed end. Upward should become downward. Yes, downward. Now it is a free end. So downward should be reflected back as downward. Now downward reflecting from fixed end is going to be what? Upward. So now I don't think I need to explain what I am going to say. I will say that blindly. If the reflection is from a fixed end, if the reflection is going to be from a fixed end, how much ever is going to be crossing, that much reflected gets produced. See, if half of the pulse is going to be, then how much is produced? The same half of the pulse has been produced. Okay. How much ever crossed, the same amount is going to get produced. Now this section has both the waves. So an upward pulse will be reflected back as, once the complete pulse is going to cross, once the pulse is going to completely cross, if complete upward pulse is going to cross, then I get a complete downward pulse traveling in this direction. So if the incident pulse is going to be, some A sine omega t minus kx, then we have a wave traveling in what? Negative x direction, and its amplitude is what? Onto the negative side. So I should write minus A sine omega t plus kx. So upward pulse directly is becoming downward pulse. So I can write the reflected one to be what? A sine pi plus omega t plus kx. So you have got pi, right? If you take the reflection is taking place at x is equal to 0, then the phase is omega t. Here the phase will be pi plus omega t. So this one has an extra phase of pi. So transverse wave reflected from fixed end, suffers a phase change of pi. Okay. Now, what about reflection from free end? I already said to you, right? Reflection from free end is going to be what? Upward pulse will be reflected back as upward pulse. Upward pulse will be reflected back as upward pulse. 1 second, I'll answer all your doubts, but after this theory. I can see some text in the chat box. I'll talk about them. So an upward pulse, once it is going to completely cross, it will be an upward pulse only. It will be an upward pulse only. How it is going to be traveling? It will be traveling like this. So an upward pulse is reflected back as upward pulse. So basically, if the incident one is going to be A sine omega t minus kx, so the reflected also has the same amplitude thingy, and you have sine omega t plus kx. It's a wave traveling. So the phase change over here is 0. There is no phase change. So whenever reflection is going to be from free end, there is no phase change. The phase change is going to be what? 0. Now you might have a doubt. Will we have perfect fixed ends and perfect free ends in reality? No, right? Perfect fixed ends and perfect free ends in reality are not possible. What is a perfect fixed end? No matter what you do, that particle should not move at all. Man, even if you are going to keep that particle inside the wall also, slightly it will move. And there is no such thing which is going to have zero mass. Perfect free end will not be there. Even if you take it to be a ring will have definitely some amount of mass. So perfect fixed ends and perfect free ends don't exist in reality. Right? So what we are going to have is, we are going to have reflections from fixed denser mediums and rarer mediums. So what is that? Look, we have one wire and we have one thick wire or thick string. So as this has more mu, you take this to be mu1 and this to be mu2, we can clearly see that mu2 is more than mu1. So automatically speed in the second one will be less than the speed in the first one. So wherever the speed will be less, we call it as denser medium. Wherever the speed is going to be more, we call it as rarer medium. So when I send an upward pulse, when I incident a pulse like this, when I am going to be incidenting a pulse like this, so when it is going to get reflected, the reflected one is going to be downwards and there will be a transmitted one. Obviously some transmission will take place. So the amplitude of the transmitted is this and the amplitude of the reflected is this. Now how do I know how much is the amplitude of the transmitted, how much is the amplitude of the reflected? It is going to be this. This they have taken it to be AU. The AU, whatever you see, is the amplitude of the incident one. After that I get some amount to be transmitted, some amount to be reflected. We can actually derive this. Now keep in mind, if V2 is going to be less than V1, if V2 is less than V1, this is negative, right? Indicating the reflected amplitude, whatever, or the reflected wave is going to be a downward pulse. If you send an upward pulse, if V2 minus V1 turns out to be negative, that's an indication that this AR, whatever we are talking about, is downwards because it will be negative. So this formula is valid for reflection from denser medium and is also valid for reflection from rarer medium. That means you flip the sides, right? You draw the thicker one this side, you draw the thinner one this side, and you send the wave from the thicker one. Then that transmitted amplitude, reflected amplitude will be still given by this. Always keep in mind V1 and V2. V1 is the velocity in the first medium. V2 is the velocity in the second medium. That you have to keep in mind. V1 is the velocity in the first medium, V2 is the velocity in the second medium. That you have to keep in mind. Okay. Fine. Now let us talk about standing waves. This is what we were working hard till now. This is the exact thing we were looking for. On string, right? So I'll take string fixed at both ends. If I am going to talk about string fixed at ends, if I am going to talk about string fixed at the ends, I have a small question, man. If the wave that I am going to be incidenting is going to be a sine omega t minus kx, then the wave that I am going to get is going to be minus a sine omega t plus kx or not, because we are talking about a string fixed. If it is fixed, the ends are fixed. So that means, for example, for you to feel what I am talking about, I will take a string like this. It's a string fixed at both ends. Let us take the length of it to be some small l, length, and the tension in it to be some t. We will talk about all of them later. Now, net displacement of the particle will be what? The net displacement or the resultant displacement is going to be the incident one plus the reflected one. So what is happening over here? You have a sine omega t minus kx minus a sine omega t plus kx. I think I can take a common, then I can write this as sine omega t minus kx minus sine omega t plus kx. So I can use sine c minus sine d formula over here. What is sine c minus sine d? Sine c minus sine d is going to be 2 cos c plus d by 2 sine c minus d by 2. So let us write that. So the resultant is going to be 2 cos c plus d by 2. That means this plus this by 2. That means 2 omega t by 2 is omega t. Okay. Sine c minus d by 2 omega t minus kx minus omega t plus minus kx by 2 means it will be minus 2 kx by 2. So you get minus kx. Man, this is perfectly suggesting what we have got. Do you remember the simulations, whatever I have shown to you? If I am going to talk about particle, if I am going to talk about particle at x is equal to 0, the moment you put particle at x is equal to 0, the resultant displacement is going to be 0 times cos omega t. So it won't oscillate at all, because as this part is 0, 0 into cos omega t will be what? 0 all the time. So that means the particle at x is equal to 0 is never moving. Now, particle at x is equal to lambda by 4. You put lambda by 4. The resultant is going to be what? Minus 2a, man, sine k. K is 2 pi by lambda. 2 pi by lambda into lambda by 4 is sine pi by 2 into cos omega t. So the particle which is at x is equal to lambda by 4 has maximum amplitude of oscillation. Man, what is the amplitude of oscillation? It's 2a. The one which is at x is equal to 0 has amplitude 0. So I can say that the resultant amplitude whatever is there, I can simply say it to be minus 2a sine kx. This is the resultant amplitude of all the particles. This represents the amplitude of oscillation, and this is going to give you the displacement. Now you see, different x values will have different amplitudes. Is that what the simulation has shown us? One last time I'll show you that. Because your conceptual understanding will improve. You look at this, resume it. You look at different particles have different amplitude of oscillations. Look at this particle. This particle is having only small amplitude. Look at this particle big. Look at that particle even bigger. So different particles are having different amplitude of oscillations or not. Even math is suggesting that. Simulation is suggesting that. Even math is also suggesting that. Right. Now I want to locate all the nodes, man. I want to look at all the nodes. I will answer all the doubts when the concept is done. You just wait. Please concentrate on what is being taught. I will answer before I end the session. Pakka for sure I'll clear all the doubts. Okay, now look. What are called as nodes? Nodes are those locations which are going to have amplitude of oscillations to be what? 0. That means sin kx should be what? 0. That means what should be the kx value? 0, pi, 2 pi, and so on. For your kind information, what is k? 2 pi by lambda. Take it to the other side. So the locations of the nodes: 0, lambda by 2, 2 lambda by 2, 3 lambda by 2, and so on. Okay. Now I want to talk about antinodes. What are antinodes? Represented with an. Those are the ones which have their resultant amplitude maximum plus or minus 2a, right? So minus 2a sin kx can be plus or minus 2a, indicating sin kx can be plus or minus 1. So for what values? Pi by 2, 3 pi by 2, 5 pi by 2, and so on. So what are the positions where the amplitude of oscillations is maximum? Lambda by 4, 3 lambda by 4, 5 lambda by 4, and so on. Now I want to mark all those locations, man. I don't want to leave them. We have a string. Okay, that string is going and it is fixed on the other side also. If I am going to talk about x is equal to 0, whom we have node. X is equal to lambda by 4, we have antinode. Lambda by 2, node. 3 lambda by 4, antinode. 2 lambda by 2, again node. So let me mark all of them. This is a node. This is an antinode. This is a node. This is an antinode. This is a node. Now I know that this doesn't move at all, but this is going to move maximum. So how much it is going to move? I will envelope it. This is how you see the representation of standing waves. Do you know what actually this means? Standing waves will be represented like this, right? The actual meaning of this is because of this. So the particle which is going to be over here, it won't have this much amplitude, na? It will have its amplitude of motion like this. So it will be enveloped only in this region. It will be oscillating only in this region. So if they are going to talk about some particle over here, it will have its amplitude of oscillation this much. So that envelope is giving you information about the amplitude of oscillations of different particles. Okay. Now, can you give me some important observations? When you look at what is distance between successive antinodes and nodes? Distance between successive nodes. What is distance between successive nodes? Distance between successive nodes is lambda by 2. Now we have one antinode here, one antinode here. What is the distance between them? That is also lambda by 2. So distance between successive antinodes is also what? Lambda by 2. And what is the distance between successive node and then antinode? It is lambda by 4. You look, node here, antinode here. What is the distance between them? Lambda by 4. Okay, super. Next. Let us talk about for what frequencies we are going to get the standing waves in a string fixed at both ends. String fixed at both ends. String fixed at both the ends. String fixed at both the ends. Now look. Man, we have a situation here. What is that situation? Pakka, it should be a node here and it should be a node here. How do I know that? Because those are 2 points which can't move. If there are 2 points which can't move, then pakka it should be nodes only, na? So once I create a disturbance, it gets reflected. So like that, there will be two waves traveling in opposite direction. One which we created, one which is getting reflected. Okay, now it is mandated that it should be node and node, right? So the first possibility is going to be them being two successive nodes. So in that situation, let us take the length to be L, and distance between two successive nodes is how much? Lambda by 2. So lambda by 2 is L. So the lambda is going to be what? 2L. We know very well that the frequency is going to be what? V by lambda. So it is going to be V by 2L. And this is the very first frequency that is possible. That's why we call this as fundamental frequency. We call it as fundamental frequency. Now, whatever the integer we are going to be multiplying to the fundamental frequency, there is one more name given to it. It's called that harmonic. Whatever the integer you multiply, it is that harmonic. What I mean, so what did I multiply to this one? I have multiplied 1, right? So whatever the integer you multiply to the fundamental frequency, we call it that harmonic. So it is called as first harmonic, right? Next, what is possible, man? Let us see. What's the next thing which is possible? See, one thing is mandatory that there should be node at the points where you have fixed. There should be node at the points where we have fixed. So definitely there should be a node here and there should be a node here. That is for sure, right? Now these nodes might not be two successive ones. Already successive ones we have dealt, na? Might be they are next to each other, next to each other. That means there is one more node in between. Then you will have the standing waves forming like this. It is the very same length of the string, right? But the wavelength has changed. So 2 times lambda dash by 2, because distance between two successive nodes is lambda by 2. I am taking the new wavelength to be lambda dash. Is going to be what? L. Then lambda dash will be 2L by 2. Then the new frequency f dash is going to be V by lambda dash. Why I didn't change V? Why did I keep it as V only? Why not V dash? Because speed of a wave is root T by mu, right? As long as I don't change the tension in the string, as long as I don't change the speed, then as long as I don't change the string, that is mu, as long as I don't change the tension, then the V will not change. Okay. Then the f dash is going to be V by 2L by 2. So the f dash is 2 times V by 2L. What is the integer we have multiplied? What is the fundamental frequency? Fundamental frequency is V by 2L. And what is the integer we multiplied? 2. So this is called as second harmonic. And one more thing, this is the first sound or vibration you can get. The first vibration that is possible for standing wave. And this is the first extra sound that is possible, right? Or you can say first extra vibrations that is possible. You remove that extra and keep it as over. So we can call this very same thing frequency as first extra tone, right? So we can call it as first overtone also. So these namings are important. I'm trying to keep it as logical as possible. I'm trying to keep it as logical as possible. Why it is called as first overtone name. Okay. Okay. And sometimes this is also referred to as 0th overtone. Because this is before first overtone, sometimes it is referred to as 0th overtone. Keep that also in mind. Now you realized what kind of frequencies we are going to get, man. The frequencies we are going to get okay. Let us see one more. We have space anyway. We have space anyway. Same length, right? We have a string, the very same string. I know that pakka this should be a node. I know that pakka this should be a node. Successive nodes is done. One node in between is also done. Next possibility is what? Having 2 nodes in between. So one node here, one node here. And then the type of standing wave possible now is going to be this. Right? So this length is L only, right? Now let us take this new length, whatever is going to be there, is 3 times lambda double dash by 2, because the new wavelength is obviously smaller when compared with this. This is a big loop, so big wavelength. Then the loop size decreased, wavelength decreased. Then the loop size again further decreased. That's why I have taken new wavelength is L. So the lambda double dash is going to be 2L by 3. 2L by 3. Now the frequency is going to be V by lambda double dash, which will be 3 times V by 2L. So we can call it as what? Third harmonic, because whatever the integer is going to be multiplied to the fundamental frequency, we call it that harmonic. And this is the second extra thing which you get. So we also refer to as second overturn. So from here, it is very evident that the frequencies for which standing waves are possible are what? First is V by 2L, next is 2V by 2L, and the next is 3V by 2L, and so on. So it is 1 is to, 2 is to, 3 is to, and so on. And one more thing, for V by 2L it is possible, and for 2V by 2L it is possible. For no other frequency in between. For you to understand, example, if V by 2L is 100, then automatically 2 times V by 2L is going to be what? 200. For no frequency between 100 and 200, for no frequency between 100 and 200, standing waves are possible. This is one interesting thing, man. This is one interesting thing. Why? Why it is interesting? If I am going to talk about traveling wave, I can create with whatever the frequency I want. It all depends on my hand. See, if this is the string, I'll hold on to this string and I'll just keep it moving up and down. If I move faster, higher frequency. If I move slower, lower frequency. So traveling wave is possible for any frequency. Traveling wave is possible for any frequency, right? But standing waves are not possible for any frequency. Sir, why is that happening? Because there is a condition that has to be met. What is the condition that has to be met? Pakka, here and here nodes have to be formed. So for the nodes to get formed exactly at those two places, there are only certain frequencies which are capable of producing nodes at those two places. So one biggest difference between traveling wave and standing wave is that traveling waves are possible for all the frequencies, but standing waves are not possible for all the frequencies. This is one important thing which you people should keep in mind. Okay. Now, application of this is going to be sonometer. I hope every one of you have done sonometer experiment. It looks something like this. We have some weight which is going to be hanging, and then we have a string where you are going to have two movable bridges. Okay, so these movable bridges, whatever are going to be there, this is the proper cross-sectional view of the diagram. What experiment we are going to do is, we take a tuning fork, right? We strike the tuning fork and we keep it on the frame, right? And we will have a paper rider on it. Paper rider is nothing but a V-shaped paper. You take small paper, you bend it in a V shape and you keep it on that. It's a paper rider. So we take a tuning fork, we strike it, we keep it on the table. Then the disturbance of the tuning fork will go into this sonometer, that is into the wire also. But if the frequency of the wire, the frequency with which the wire is going to be oscillating, can you see green dots? No, we'll go for blue. Because on these movable bridges, those points can't move. So it's a node. So the string will be oscillating with its frequency in such a way that node and node will be formed. Once a disturbance is created, that means the string has to move. So string will move with its own frequency where a node and node gets created over there. Now if the frequency of the tuning fork and the frequency of oscillations of the string, if both of them match, that's resonance. In resonance, what will happen? The paper rider, or in resonance, what will happen? Amplitude of oscillations will be bigger. If the amplitude of oscillations are bigger, what will happen? The paper rider falls off. So if resonance is not taking place, paper rider won't fall. If you have done the experiment, you people could have clearly understood this. If you have done the experiment, you could have clearly understood. You'll strike the tuning fork, you'll place, paper rider won't fall. That's an indication the tuning fork frequency and the frequency of oscillations in this are not same. So then you will adjust those movable bridges. Then again you will strike the tuning fork, you'll keep. Paper rider doesn't fall. Again you will adjust, you'll strike, you'll keep. Paper rider falls. If the paper rider falls, that means the frequency of oscillations in the string and the tuning fork are same. That's what is going to be called as resonance, right? So how do we generally do the experiment? I'll just show you that. The movable bridges, whatever are there, they are going to be first kept very close, and we have the string. Take this to be the string, right? Only a part of the diagram I am drawing. So we keep a paper rider, right? The paper rider also, I'll draw it here. Now slowly we will increase the separation between those wedges or movable bridges. Slowly. So then let us say for this length, for some L1 length, the paper rider has fallen. Indicating what? The frequency of oscillations here and the frequency of the tuning fork are same. Let us say here node and let us say here node. And what is the very basic thing that can get formed? these being two successive nodes. So then what will happen? Your L1 is going to be lambda by 2. How do I get the lambda? Okay, fine. First of all, what is the lambda? 2 times L1. Now you tell me what will be the frequency? Frequency is going to be V by lambda. So the frequency of oscillations will be what? V by 2L1. And how do I know the frequency of oscillations? It's same. If the paper rider falls, frequency of oscillations and the tuning fork should be what? Frequency of oscillations should be equal to the frequency of the tuning fork at resonance. So that's it. So the frequency of the tuning fork, we can write it to be what? V by 2L1, and that V is going to be what? Speed of the transverse wave in the string, which is going to be, speed of the wave in the string, which is root T by mu, is 2, is this 2 times L1. You can write like this. So using this, you can verify the tension, you can verify the mass per unit length of that string. L1 anyway is going to be a measured one, Ft. But keep in mind, you have to do like this. Like very slowly you have to increase the separation. You can't keep them to be at a big separation and say that these are two successive nodes. No. Now, if you want to further continue the experiment, as you are using the same tuning fork, that means the frequency, again resonance is going to take place, will not change. Speed will not change. And the wavelength also will not change. If F doesn't change, V doesn't change, lambda also should not change. So what is the next separation at which it is going to take place? The next separation of the movable wedges or movable bridges. If I am going to take it to be some L2, the next separation, man, what I realized is that as I am using the same tuning fork, so at resonance, frequency of tuning fork, frequency of vibrations will be same. That means F is kept same. V is kept same because I am not changing the tension. If F is same, V is same, lambda should be same. That means the size of the loop should be same. That means I should get next thing as 2 loops of same size. Yes, condition is also met. Node here, node here. Then what will be L2? L2 is going to be 2 times. I can write confidently, I can write it is lambda by 2 only, not some other lambda dash or something. I don't need to write like that. Okay. So the frequency is going to be what? V by lambda, which is going to be what now? V by L2. Or, yes, V by L2. So that frequency can be written as root T by mu divided by L2. But which has more importance in competitive examinations? This has more importance in competitive examinations. Reason being, we keep them very close and then we start separating very slowly. And this is the fundamental mode of oscillation. Fundamental mode. When you are talking about two nodes and if there are two successive nodes, we are talking about fundamental modes. Keep that in mind. Okay, I'll do it, Rangaswamy. I was waiting for the notification to come out. Notification has come out. Now I'll do it. Okay, last man. I think 1, 2, 3, 4, 5. Okay, 5 questions are there, out of which 2 of them I'll do. My brain got saturated. I'm teaching continuously from 2:10. You can say 2 o'clock onwards. I'm teaching continuously. My throat, it's paining a bit. A guitar string of length 90 centimeter vibrates with a fundamental frequency. Man, guitar string means what? It's a string fixed at both ends, right? So what is the fundamental frequency of a string fixed at both ends? It is V by 2L. That's it, blindly. V by 2L. Right, is 120. They are asking length. Sorry. They are giving V indirectly. F is how much? 120. V by 2 times 90. Are we going to talk about the same V? Yes. we will talk about the same V. So the V is going to be 120 into 2 into 90. Right? Now, if you are going to be changing if you want to change the fundamental frequency by maintaining the same tension in the string, then the new fundamental frequency is going to be V by 2L dash. So that is given as 180. V is how much? 120 into 2 into 90 divided by 2L dash. So 2 gets cancelled out, 92s. So the L dash is going to be 120 by 2, which is going to be 60. Which is going to be 60. Okay, this is the first one. The next, fundamental frequency of vibration of a string stretched between two rigid supports, 50 Hz. So again, fundamental V by 2L. Okay, mass of the string is 18 and the linear mass density is 20 gram per meter. The speed of the transverse wave so produced is, man, frequency is how much? 50. V by 2 times length. Did they give length? No, they gave mass per unit length and they gave mass. So mu is going to be what? Mass per unit length. So length is going to be what? Mass by mu. M is how much? They have given it as 18 grams. By how much is this? 20 grams per meter. So it will become 18 by 20 meters. So it is going to be what? 9 by 10 meters. So you got length. So it is 9 by 10. So you just go and multiply. It is going to be 50 into 18 by 10, which is going to be how much? 90. So the speed of the transverse wave is 90. So the fundamental frequencies are very important for you to memorize. Fundamental frequencies are very important to memorize. In an experiment with sonometer, when a mass of 180 grams is attached to the string, it vibrates with a fundamental frequency of 30. See, whatever the mass is going to be attached to the string, it is going to maintain tension. So the fundamental frequency is going to be V by 2L, where the V is going to be root T by mu divided by 2L. Okay. When a mass small m attached, the string vibrates with fundamental frequency. See, basically, they are changing the tension. So the frequency is root mg by mu by 2L. So if mass changes, fundamental frequency changes. So F1 by F2, I can write it as root M1 by M2. What is your M1 man? 180. What is your this thing? They have added one M mass, so which is going to be 180 plus M. And what is F1 by F2? 30 and 50. So you can say 30 and 50, which is 3 by 5. So it's 9 by 25 is 180 by 180 plus M. So this is 20. So you will have 180 plus M to be equal to what? 25 into 20, which is going to be 500. So the M value is going to be how much? 500 minus 180, which is going to be what? 320 grams. So if the mass is going to be, like, if you add 320 grams more, then you are going to get the fundamental frequency changed to 50. So these are the type of questions they are asking these days. With this, we are going to end the session, right? If you have any doubts, you just ask, Sir, Vedantu JEE Telugu Law, Mechanical Properties of Fluids. I will be doing mechanical properties of fluids in that channel. You don't worry, man. Okay. If you want to ask anything, please ask regarding examination or some tips or whatever it is. Otherwise, I'll end the session. If you love the session, if you have loved whatever the simulations I have shown, if you have loved it, whatever the content that has been done, do make sure to like the video. Hit that like button. Notification has come. Yes. Yes, DG, VC, CV, GC. Notification has come. Syllabus hasn't changed. Syllabus has remained as it is. Syllabus has remained as it is. Nothing to worry. Also, sir, mechanical properties of solids. Yes, whatever I have done in mechanical properties of solids is enough. Yes, Mr. Yash, it's enough. Okay, bye then. Bye then. Good night. Even I am tired a bit. Good night.